Thank you for the introduction. I start with a slide as we got the invitation to hold this talk. We had this here already in our lab. What you see is a nice logo of the Wacken Open Air Festival made with high strength steel, and we made it for a befriended company as a gift. But however, we thought it would also fit this purpose well, and yeah, it was a nice picture. Okay, you heard already about myself, my research interest. However, I added a picture here because the quality of the camera is sometimes not so good. So this is me in the green world. Okay, so I'm going to cover 3 points. One quite briefly, but the others a bit longer. Effects when welding ultra high strength steels, importance of mean stress for fatigue of welds, especially with regard to higher strength materials, and what's different in comparison to normal strength steels. And then we have evaluated fatigue with imperfect welds, and that will be the last point. So when welding steels, especially the carbon steels, low alloyed steels, we observe changes in the microstructure, because what we basically do is we do an uncontrolled or more or less uncontrolled heat treatment of the base material. So when we apply welding, we do not only alter the weld itself, we also alter the base material, and that of course can be an issue, especially if the material itself has gained strength through heat treatment. So what we need to do is we need to qualify our welding process in the matter that this unwanted heat treatment of the base material does not harm the material too much. Of course, this is more or less done by a trial and error principle. And what you basically do most of the time, you control the cooling during your welding by controlling the heat input. So the travel speed, also welding energy, and also interpass temperature is controlled to basically to fit the cooling times to the material. And what we want to avoid is we want to avoid too short cooling times, because what's happening then is cold cracking just from high hardness. And if we apply too much heat, we may observe brittle fracture from loss of toughness. And so there is a sweet spot. It's not ideal always, but it's more or less the best point when trading off one for the other. And that is what we are aiming for when welding ultra high strength steels. Of course, this is different for every steel grade. Just to show you how complex it can be, or it can become, I have looked at a data sheet for an S1100, so a commercially available high strength material by Dillinger. And I just took this from their data sheet. And what you see here is they recommend a preheating temperature depending on the sheet thickness. And that, of course, needs to be controlled. So not too cold, not too warm. Also, preheating needs to be limited. And interpass and working temperatures are limited, for example, here, because if you have too high temperatures, cooling times would be too long and you lose your toughness. So anyways, the heat input should be reduced to reach cooling times below 12 seconds, because if it's longer, you also lose strength. And if the base material in the heat affected zone becomes softer than the weld or the other base material, then we have an issue. Of course, when looking at this material S1100, we must say that we don't have a filler metal with matching strength yet. So what you do is basically you use the best filler metal that you have, and you just follow these recommendations. So there's also a recommendation on that. Best is to place welds where structural stress is low, yeah, and use the highest strength filler material that is available. We also heard about hydrogen today. Of course, hydrogen cracking is an issue, so we are recommended to use filler metals with reduced hydrogen content. And in case of large restraint at high residual stress, we are recommended to apply a heat treatment after welding. And that is around 200 degrees C for several hours, also depending on the sheet thickness. So we have a high residual stress issue, especially when the components are stiff. But however, thermal stress relief is prohibited because that also alters the material strength. And no thermal straightening is allowed because that is in danger also as an unwanted heat treatment, and some effects may occur like softening or loss of toughness. So what we see when welding these materials, it's a bit difficult to do, and the entire topic is also not easy to manage. And we see that in the welding industry that this task is more or less fulfilled by experienced companies. So not everybody can do it because that's just so difficult. When talking about residual stress, of course, restraint is really important. And what we see is that we have normally in stiff structures, usually the situation that we have very high restraint. And with very high restraint, we see that the residual stress also over thickness of such welds becomes really high. And in this case, that investigation investigated S360 materials, so that was in the magnitude of the yield limit. If we have lower restraint, then it becomes less with residual stress. And of course, if investigating residual stress effects in the laboratory, usually the problem is that you have low restraint, because what we do is we weld small scale specimens with low restraint perpendicular to the weld, and the result is low residual stress. And when investigating residual stress effects, and you have low residual stress, of course, that's difficult. So what you need to do when you are in interest of investigating residual stress effects in high strength steels, you need a specimen that has component character, although it is small enough to be tested in conventional test equipments. So what we need is some kind of reaction force in the component itself. And the longitudinal stiffener is such a component that can be used for that. What we see here is a fatigue test specimen that I used during my PhD thesis. And we see that the crack starts here at the longitudinal stiffener, at the end of the stiffener when loaded axial. And the special thing about this is we have a small scale specimen with high restraint, so we can investigate residual stress effects. So how is residual stress treated in design standards? Basically, the idea is based on a recommendation from Gurney at TWI in Cambridge. And they basically concluded that normally on the safe, when designing structures on the safe side, usually tensile residual stress is high. And we saw that earlier from the picture of Lagarde, that is due to high restraint. And basically what they concluded from that is that the fatigue strengths of components, especially from welds with high material strengths, the entire fatigue strength is independent from the applied R ratio during fatigue testing. And this is sketched here. So you have a nominal load stress that you apply during your test. You have an R ratio of -1 or 0 or whatever, but the resulting effective stress is always higher because you have so high residual stress. And in the end, you may have some residual stress relaxation, but your upper stress during cyclic loading is always as high as the yield limit. And of course, with higher strength material, this may be higher. So what I did then during my PhD time, I investigated these longitudinal stiffeners in different conditions. And in this case, they were in the condition as welded, so containing high residual stress due to the component reaction stresses. And what we saw was that the assumption made by Gurney earlier, of course, is correct when the residual stress is high enough. What we see here is we had different test series tested at different R ratios, and we see they are more or less the same. So when sketching them in a high diagram, we see the resulting fatigue strength over the mean stress, and we see, yes, for these three test series, there is basically no difference. And the reason is, of course, the high residual stress. So basically what we can conclude here based on Gurney's assumption, the effective stress ratio when testing specimens with high residual stress is usually a lot higher than the nominal stress ratio. So, and when it comes to the different effects, so now we have thermally stress relieved samples, we see there is a difference, and that difference is quite large. And we can also plot here the Hay diagram, and we see we have mean stress dependency. So that means with increasing mean stress, fatigue strength becomes smaller. And basically also that confirms Gurney's assumption. Now, when applying the thermal stress relief, the effective stress ratio is approximately as high as the nominal stress ratio. Of course, thermally stress relieved, some residual stress may remain, and we also have some other effects affecting the mean stress, but it is quite similar, and yes, we see that we have a mean stress dependency. So here we see all the results for the conventional steel grade S355. And we see now three different conditions. So the as welded condition, the annealed condition, and then in addition, a third condition where preloading has occurred. And what I did was I pre-stretched the samples over the yield limit or until the yield limit. So these samples here were stretched to a nominal stress of 360 megapascal, resulting in larger stresses, of course, at the notch. And these caused compressive residual stress at the notch. And what we see is that in result, so with high tensile residual stress, we have mean stress independency. Without residual stress, we have mean stress dependency. But with compressive residual stress, we also have the mean stress dependency, but higher fatigue strength overall. And that is the residual stress effect. And now when we come to high strength material, we see that this effect, of course, becomes a lot larger because the compressive residual stress magnitude becomes larger when preloading, and also the residual stress becomes more stable during cyclic loading because we have the high yield limit. And what I then did, I transferred all that to the so-called effective mean stress, and by effective mean stress, I combined the cyclically stabilized residual stress together with the load mean stress. And what we see is that we get a quite nice relationship between the fatigue strength and the effective mean stress. And in this case, it does not matter anymore what the material grade is, and also what the originally tested stress ratios are. We can all distinguish the effects here by the effective stress ratios. Okay, so and then what's also important when it comes to fatigue of these high strength materials when welded, we see normally that the fatigue strength increases with ultimate tensile strength. And that is usually the effect when you test base material. However, if you start to introduce notches, you have already a smaller effect when the notches are mild. But if welded, this effect becomes even larger. So until a point where you almost have no increase in fatigue strength anymore with increasing material strength. And there is even a turn-off point where this may drop later. And yeah, basically when looking at welds, we see that we have, of course, different weld types. So we have butt welds, we have overlap joints in different configurations, and we have here transverse stiffeners, or here in this case, it's a cruciform joint. And we have, of course, an increasing notch effect here from top to bottom. And what we observe is that these welds are usually notched so high that we don't have any benefits from fatigue load. However, when welding, usually you cannot avoid imperfects. And here I have a short example that is based on these undercuts. So we have here welds made with a laser, and we see the macrographs soon, but we applied laser welding in different configurations, resulting in different weld qualities and also different undercut depth. And we applied different fatigue evaluation approaches based on effective stresses rather than nominal stresses, because the nominal stress in such a component is, of course, increased by smaller weld cross sections when the undercut becomes larger, but this does not catch the effect in total, because the effects of stress concentration in fatigue is not linear with the simple factor of a cross section reduction. So basically, we have different approaches. Most common is notch stress approaches with reference radii, but however, with such mildly notched specimens, they are not easy to apply. So we applied effective stress approaches, one based on Neuber, where you basically determine the stress along a line coming here from the surface perpendicular to the surface, and then you basically simply determine a mean value of the stress along this line. And this line has a length of rho asterisk. So, and the other one is that you have a line that has an offset to the surface, and you just simply determine the highest stress along that line. And that approach is based on assumptions made from Moore, Patterson, and Taylor. So here we see our welds. We had nice laser welds. These were basically a good quality. And we also had laser welds with varying quality. So we had here a large undercut depth, and here we had a wider weld with different weld geometry parameters, and here as well. And basically we determined typical weld quality parameters based on an ISO standard that catches the quality quite well. And we have the weld width, we have the undercut depth, we have the root recess, and we have misalignment. And we then determined all these factors, and we were able to compare them. So we then determined the stresses along the line that I just showed you, and we determined the so-called KF values, which represent the stress raising factors. And then we determined these for the entire test series for both approaches based on Neuber and Patterson, Taylor, and Moore. And then when we look at the fatigue test results, we see that 3 test series were quite comparable because the quality parameters were also comparable. However, 1 test series was really worse, and that was the one with the large undercuts, so bad quality. And of course, this effect is higher when it comes to high strength material. And yeah, basically with such data, you cannot make a structural design because the scatter is too large and the quality is not captured properly. So what we did, we applied these stress or these fatigue strength evaluation approaches based on the local concepts. And then we ended up with one population of fatigue results, and these are now or these can be used as a design value, even all samples, no matter the quality, can be evaluated by one design SN curve. So basically what you do is you put more effort in the stress evaluation and come up with a better evaluation of the results. Okay, then I'm done, and I thank you for your kind attention, and I'm open for questions.